Let's do one long example where we review the ideal gas law and their van der Waals equation and look at how these are related to each other under a variety of conditions. So in this video, we'll do a problem that reviews the ideal gas law, the van der Waals equations, and looks quantitatively at what we discussed in the previous video. Here I ask you to calculate the pressure of a 1 mole of methane gas at 2 different conditions. Additionally, I ask you to compare all of the answers. The last part of the question is going to make a bit more sense once we finish the math on the previous examples. So here we're going to start with condition 1. Let's first fill into the ideal gas law. This is a simple plug and chug, as we did in previous examples. So if we fill into PV equals nRT, solving for P, we find that our value is 1 atmosphere. Okay, so now let's do the exact same thing for our van der Waals equation. Notice I did a bit of rearrangement ahead of time for you in rearranging the van der Waals equation for P. Please make sure that you can actually do this yourself in any sort of exam or homework situation. So we fill our values in. Our 1 mole gets filled in, our R gets filled in. Remember, we're back to using liters, atmospheres, kelvins, and moles, so we go back to the 0.0821. We fill in our Kelvin and temperature, our volume, and then our A's and our B's. When we solve all of this out, we get 0.994 atmospheres. Think about whether this is expected. We are at relatively high temperature and relatively low pressure situation, and so it makes sense that our 2 values would be similar. Now let's do the exact same thing for our next example. We have our second set of conditions. So take a minute before continuing on to do this yourself. Since this is just filling in numbers, I know that I'm going really fast, but it'll do you a bit more good if you do this on your own first. So first we're going to fill into our ideal gas law. When we do this, we end up with 821 atmospheres for this set of conditions. This is a pretty high value for pressure. Now, let's do the exact same thing for the van der Waals. Again, you can go ahead and fill into the rearranged version for now, but please make sure you know how to get here yourself. So when we fill into our van der Waals equation, we get a much higher value. We get 1,810 atmospheres. Which, this is a pretty high value as well, but also notice that it's noticeably higher than 821. Even though this is for the same sample, just doing 2 different treatments. It is far, far higher than the non-ideal gas. And that's because it's taking into account non-ideality. So now to wrap this up, let's look at our 4 answers together. In condition 1, we were at atmospheric conditions, and we have almost the same answer for our ideal in our van der Waals equation. This is something that it would be reasonable to treat as an ideal gas. Now, if we increase the pressure, our answers become very, very different because our gas is not acting ideally anymore. Please make sure to note that the reason it isn't acting ideally is because of the pressure. High temperatures are actually making the gas act more ideal if everything else is equal. It's only if it's appreciably raises the pressure that it now behaves non-ideally, and so there is a little bit of competing factors in that case. So the non-ideality is caused by the extremely high pressures in this case.